Today we're going to go ahead and look at inverses, inverse functions, and a little bit with inverse relations. Now, suppose we had y is equal to 2 to the second power, and we needed to graph that. So to do that, we could go ahead and make ourselves a t-chart. I just chose some values of x, then we could plug each one of these numbers in. 3, so a 2 to the third we know is 8. 2 to the second power, you know, is 4. 2 to the first power, you know, is 2. 2 to the 0 power is 1. 2 to the negative 1, remember that means 1 over 2. 2 to the negative 2 would be 1 over a 2 squared, which would be a 1 over 4, and so on. Now, you'll notice if you're going this way, you keep dividing by 2 each time. So you can see, we had mentioned before that anything to the 0 power is 1, and you can see that that pattern shows up. You can also see as you continue to divide by 2 that the negative exponents that we talked about before ends up being related to what we were dealing with. Now, when you're dealing with inverses, basically what you put in gives you out the blue. Your inverse needs to undo that. In other words, we need to figure out what do we put in so that we get out our negative 3, because that's what we started out with. Or what do you put in to get out your 3? So your inverse table basically just switches your x and y around. What was your output becomes your input, and what was your input becomes your output, because your red has to undo it. Now, if we look at this and we graph the blue, we get that. If you graph the red, we would get this. Now, technically speaking, these functions go on forever, and so there should be an arrow here going this way, and then it goes out this way here forever. Similarly for the red, it goes out this way here forever, and then goes down this way forever. Now, your domain, once again, is any number that you can plug in. And in this case, we could plug in any number we want, so it's any real number. Your range is what you get out. Notice when you're looking at the blue, your range is how far up and down it goes. It goes up forever, but only comes down to the x-axis. So in other words, it never goes below the x-axis, so it's only positive numbers that you get out. Now, when you switch it and do your inverse, your domain is what you put in. Notice we're only putting in positive numbers. Or looking at your graph, notice that your graph only exists to the right of the y-axis where your x is positive. And your range is how far up and down the red goes. Well, it eventually would go up forever, and you can see it goes down forever, so your range is all real numbers. You'll notice for your inverse, your domain and range are flipped. When you go from your original to your inverse, they're flipped. Graphically speaking, if we take our blue reflected over the y equals x line, we get our red. So in other words, if you would fold this graph along the green line, fold the blue over that green line, it would give you the red. So that's what it looks like graphically as you're reflecting over y equals x. Domain and range, function to your inverse, they're flipped. When you're looking at your tables, the ordered pairs, the x, y columns are flipped. So when you're looking at a table of values, your x and y values are switched for your inverse. So in other words, your domain of your function becomes the range of the inverse. Or the range of your original function gets switched to the domain of your inverse. Graphically, it's reflected over the y equals x line, as we said. So how do you find your inverse? By looking at an equation or a function. Well, basically, you switch x and y because of that y equals x line, and then you solve that new equation for y. Now, an inverse function is written, if that's your original function, this is your inverse, or this, which does not equal putting that little -1 after the x. So if you're talking about inverse, that little -1 exponent has to go after the name of your function of f or g or whatever it is you're dealing with. It does not go after the whole thing. So here we're looking at basically a set of ordered pairs, which is like a table of values, but from a different perspective. So to find your inverse, you just switch your x and y, we were told. So your first ordered pair, you switch your x and y. Second ordered pair, you switch x and y. Then you switch your x and y, and switch x and y. So what we have here in red is your inverse. If you're given a function, we know that f of x really means y. If we wanted to find our inverse, we'd have to go ahead and switch x and y. Then all we have to do is get y by itself. Well, to get y by itself, I go ahead and subtract 2, and I would get this. Then I would go ahead and divide by -2 or multiply by -1/2. Would not make a difference. So you could write it as y is equal to a -1/2 x plus 2 in parentheses. You could distribute it through -1/2 x with a plus 1. You could write it also as an x minus 2 over a -2. Any of these would be appropriate ways to write it, but your final answer needs to have this written right here. No matter which one of those three on the right you chose to use, you need to go f inverse of x equals those. So go ahead and try to find your inverse on this and then watch the video. We know g of x means y equals. To find your inverse, you switch x and y. Then to try to get y by itself, you'd subtract x from, or subtract 6 from everything, and we would get this. Then to get rid of that 1/3, we'd have to multiply everything by 3. And so then we get our inverse. But because we started out with g of x, we'd have to have a g here, -1 exponent of x. And then we'd write our answer. So how do you determine if they're inverses? Well, one way you could do it is to actually find the inverse of f to see if it ends up giving you what g is. A second way is to take one function, plug it into the other function, that composition of functions. If you do that, and once again, our first one is 3/4 times input minus 1, and we're going to plug in our other function. So it's 3/4 times that other function with a -6. Distribute through your blue 3/4. Still bring down your -6, collect your like terms. If you plug one function into the other function and it simplifies down to a nice normal x, well, then they're inverses. If it does not simplify down to a nice normal, just plain old x and nothing else, they are not inverses. So see if you can determine if these are inverses. So we could take this and plug it in here. Our first function is 3 times input plus 1. Our input's going to be the maroon function. Notice when you distribute through here, timesing by 3 cancels out your dividing by 3, so you have an x minus 1. Still with that plus 1 afterwards, we do get down to a normal x, so yes, they are inverses. Looking over here, we have 2 times input plus 1. Our inputs are other function. If we distribute through, collect our like terms. It does not simplify down to a normal x, so they are not inverses.